Okay, so just a reminder, the kinetics exam is due on Friday. So if you have any questions, just let me know and we can find a time to talk about it. I should have time this week. Any concerns? Okay, good. All right, so the topic of today's lecture, we're going to keep talking about scattering processes, and today's lecture is going to be mostly qualitative. I'm going to give you an overview of different scattering processes and what they look like, and then we're going to go into more rigorous detail next week. Okay? And so the first thing that I'll talk about is different types of reactive scattering processes. So basically, reactive scattering can lead to different distributions of scattering angles, and I'll look at three examples that sort of show you representative overview of different types of reactive scattering processes. And so the first one that we're going to look at is called backward scattering. And so this is the case when you have this F plus D2 reaction that we talked about in the introduction to this section. And what do I mean when I say backward scattering? Well, if you look at the angular distribution for this reaction, and so the velocity and angular distribution that's shown here, it's already been converted to the center of mass frame. So this is the distribution of HF molecules in the center of mass frame. Right, and so the contour plot is just showing you the probability of finding a HF molecule, right, the product, with a certain velocity vector in this two-dimensional plane. And in the center of mass frame that we're using, the fluorine atom is coming in this way, the deuterium molecule D2 is coming this way. And when we say it's backward scattered, what we mean is that the fluorine rips off a deuterium atom, and then the product scatters backwards in the direction in which the encroaching fluorine atom came in, right? Okay, and so on this diagram, there's these dashed circles, and each dashed circle, based on conservation of energy, that corresponds to the maximum velocity, which would be consistent with production of the DF product in different vibrational levels, right? So if you produce DF in V equals 1, then this is the energy that it would have. If you produce it in V equals 2, it should have this energy. V equals 3, this energy, right? So the more internal energy the DF product has, the less energy is available as translational energy of the product. So higher V corresponds to a smaller velocity vector. Okay, does that make sense? And remember, when we introduced this reaction, one of the motivations for studying this reaction was because it can be used to make a chemical laser. And so you can see directly from this diagram that the population distribution is inverted. So there's more intensity, for example, in V equals 3 than there is in V equals 2. Right? And so you can get that information directly from doing this experiment where you measure this angular and velocity distribution, because you can assign, based on the energy conservation, you can assign this peak to V equals 3 and this one to V equals 2. Right? Because the products appear at different velocities. Okay? So why is there intensity located inside the dotted circle? Well, the answer to that is these dashed lines were drawn considering only the vibrational energy, but you can also have rotational levels of DF product that are excited, and if you have rotational excitation in addition to vibrational excitation, that means there's even more internal energy in the HF molecule, which means that its final velocity is going to be shifted a little bit less. Right? So the further you are inside each one of these circles, that means you have more rotational energy in the HD. Okay? Any questions so far about that? Okay, so based on this diagram, we know a lot about the angular distribution of the products, and we can also assign different vibrational levels based on the energy conservation. Okay, so what does this mean that the scattering is occurring in the backward direction? What does that tell us about how this reaction occurs? Well, basically what that says, so let's say you have a D2 molecule and an F atom. So forward scattering is most likely to happen when you have a high impact parameter. That means when the fluorine sort of goes past the D2 molecule with a large amount of space between them, right? But if you have a low impact parameter corresponding to direct head-on collisions, that's where this reaction is more likely to occur. And so trajectories that lead to extraction of a deuterium are also very low impact parameter collisions. And so by conservation of momentum, if you have a low impact parameter collision, you're more likely to scatter back in the direction that you came from. Okay, does that make sense? So the F has to really collide with the D2 head-on, extract a deuterium, and then it scatters backward. Okay? All right, so the next example that we'll look at is sort of the opposite of that. So in this example, well, it looks the same, but if you look at the axis system, it's drawn the other way around. But this system is potassium atom reacting with an I2 molecule, right? Molecular iodine to make Ki plus I. And this is an example of a forward scattering reaction, also known as a stripping reaction. And so what I mean by that is, in this case, this K atom, which is attacking the I2 molecule and removing an iodine, the way that this axis system is drawn, the K is coming in this way, the I2 is coming this way. Again, this this velocity vector probability diagram is, it's already been corrected to the center of mass frame, right? So the, zero velocity in the center of mass frame corresponds to this point here. And in this case, the Ki comes off in the forward direction. So the K does not get repelled back in the direction that it came from after it extracts the iodine. It keeps going forward, right? So it kind of goes forward, it strips off an iodine atom, and it leads to a Ki that's going in the same direction as the attacking potassium atom was originally going. Okay? Okay, and so this is an indication when you see forward scattering, that means that probably the reaction occurs at large impact parameters. By the way, are you familiar with the term impact parameter?
Yeah. Okay,
good. Because we went over that in the kinetics class, but I don't remember if I did it in this particular class. Okay, good. So probably the reaction occurs at large impact parameters. In this particular reaction, the reason for that is that this reaction follows what's called the harpoon mechanism. And so in the harpoon mechanism, basically what happens is, at a relatively large distance between the potassium and the iodine, there's an electron transfer from the potassium to the iodine, and basically you make I minus and K plus, right? Because, or I'm sorry, this is I2, right? Because iodine atoms are highly electronegative. Potassium is a metal. It has a very, it's easy to strip off an electron from a metal, right? So this electron transfer happens at relatively large distances, and then there's a Coulomb electrostatic interaction which draws the two molecules together so that they can react. And so what that means is, you could have large impact parameters, right, where I2 is going this way, K is going this way, right? And then after this electron transfer happens, right, you get K plus and I2 minus, and then they attract each other, leading to a reaction forming Ki, and the K keeps on going in the forward direction, right? You don't need this situation which you had in the other case where you have a really direct head-on collision, right? This was what leads to backscattering, right? This type of situation. Okay. And so the reason why it's called the harpooning mechanism is because there's an analogy to catching a whale or a big fish with a harpoon, right? Because if you think of the electron as being like a harpoon, basically the potassium atom harpoons the iodine molecule by shooting its electron at it, and then after the electron is stuck to the I2 molecule, the K plus harpoons the, right, it reels the iodine molecule in so that they're close together, they collide and they react. That's why it's called harpooning. Okay, any questions about that? Okay, so different reaction mechanism leads to different scattering distribution, so you can already see, how this type of information is really interesting and useful for learning about how the reaction happens. Okay, and then a third example that I'll talk about is a reaction that leads to basically a forward-backward symmetry. So if you look at the forward side of the scattering distribution versus the backward side of the scattering distribution, they look symmetric. There's an equal probability of scattering forward and backwards. And in this particular case, the reason why that happens is because the reaction involves what's called a collision complex. So shown here, this is data for O plus Br2, right? So forming BrO plus O. And the way that this reaction happens is basically there's this OBr2 reaction complex, which is relatively long-lived, right? So O interacts with Br at a short distance, and it forms a complex that rotates around. And it takes more than one rotational period in order for the reaction to happen on average. And so that's kind of like, let's say you have an A and a B molecule, and each one jumps on opposite sides of a merry-go-round, and then, after the merry-go-round goes around a few times, they sort of randomly, after a certain amount of time, decide, okay, now we're going to get off. And, as long as the reaction is slow relative to the period of rotation of the merry-go-round, then you're going to get off in sort of a random orientation relative to the initial orientation that you were in when you first got on the merry-go-round. Does that make sense? Okay, and so you might think, well, shouldn't the distribution then, the angular distribution, it should be, every angle should have exactly the same probability, right? And that's true if you consider a particular plane, but remember, in a scattering experiment, you don't control, so you can control the relative velocity direction, but you cannot control which direction the impact parameter is in, right? So it could be in this direction, meaning you rotate in this plane, or it could be in this direction, meaning you rotate around in this plane. So you're rotating around in some plane that contains the relative velocity, but it could be any plane. And the scattering is always cylindrically symmetric about the relative velocity vector, right? We mentioned this last time. And basically, if you get off at any point on the merry-go-round, then you have to add up all the azimuthal angles, right? You have to rotate this way and add up all the possible trajectories. And it turns out there's many trajectories, right? Every single merry-go-round, whether it's this one or this one or this one or this one, they all include this direction and this direction, right? But only the one that's in this plane includes this direction, right? If you rotate it away, then you're going in that direction. And so that's why it's basically a geometric factor that leads to this the situation where the forward and backward directions have more probability than the 90-degree direction. Does that make sense? Okay. Okay. So in summary, we looked at just qualitatively different results that you can have from reactive scattering experiments. These give a very detailed picture of how the reaction proceeds, and in fact you can use the data. If you analyze it quantitatively, you can learn a lot of information about the potential energy surface for the reaction. So we looked at 3 examples. One is a rebound reaction where you have a very small impact parameter leading to sort of a rebound of the reactant back in the direction that it came from. The other example was where you have a stripping reaction where the reaction can happen at relatively high impact parameters. In the case that we looked at, it was because of the harpoon mechanism. And that leads to forward scattering. Or if you have a relatively long-lived interaction complex between the two reaction partners where they basically stay bound to each other for a period that's long relative to the rotational period, then you have what's called a collision complex, which leads to a backward-forward symmetry. Okay? Any questions before we move on? Okay, so the next topic, this pen wasn't so good, I'll use this one. Okay, the next topic that we'll look at is non-reactive scattering. Okay, and in general there's two types of non-reactive scattering. Non-reactive scattering can be either elastic or inelastic. So I'm sort of following now Houston section 843, if you want to read along in the textbook. And this is on inelastic scattering. Okay, so inelastic scattering basically means that I'm sorry, I'm out of order. First we're doing elastic scattering. Sorry about that. Yeah, so first elastic scattering. Elastic scattering means that the energy of the products is the same as the energy of the reactants, right? And so basically, that means you have two collision partners, they don't undergo a reaction, right? So the final masses and the initial masses are the same when you have non-reactive scattering. But in the case of elastic scattering, also you do not have any excitation of internal degrees of freedom, so that the final translational energy equals the initial translational energy. You end up in the same internal states that you started with. Okay? And so the distribution of scattering angles in favorable cases can be used to calculate interaction potentials. Right? Elastic, as I mentioned, this means there's no reaction and no energy transfer. Okay? And so therefore, the final energy is equal to the initial energy, right? The final kinetic energy is equal to the initial kinetic energy of the particles. But the direction of motion could change. Okay? And so this is the type of scattering, so like for example, if you have two billiard balls scattering from each other, this is a very close approximation for an elastic scattering process, where you just, in the lab frame, you can transfer momentum from one object to the other, but you don't excite any rotations or vibrations. You just transfer basically linear momentum. Okay? And so in the case if we look at the Newton diagram, if we have two particles, one in the lab frame with velocity v1, second one with a lab frame velocity v2, then as we discussed, the relative velocity is just v2 minus v1, right? So this is vr, and the center of mass velocity always intersects this relative velocity in the lab frame diagram. And so the relative velocity component of particle 1 is shown here. And this has a magnitude of m2 over total m times the relative velocity. I'll put that inside the output value. Okay? And so if you're doing an elastic scattering, that means that the total momentum, so the relative momentum does not change, right? Because there's no energy transfer, but the direction could change depending on the impact parameter and the potential energy surface for the interaction. So that means that the scattering product is going to be found on a Newton sphere that basically looks like this. It's just a perfect circle drawn about the center of mass with the radius of the original relative velocity. Right, so this is the Newton sphere for particle 1 in an elastic scattering process. Okay, does that make sense? So it's relatively simple. There's only one energy that's allowed, but the direction could change. And of course, if particle 1 scatters this way in this diagram, in order to conserve momentum, right, in the center of mass frame, the momentum is 0. So the other particle would have to be exactly in the opposite direction. But as long as the two particles are canceling each other, they could be canceling each other in any direction. Okay, so this type of scattering is very common when you have rare gas atoms scattering from each other, right? Because rare gas atoms basically look like billiard balls. It's very difficult to excite internal degrees of freedom, right? You'd have to have very high energy collisions in order to excite the electronic states of an atom. But let's look at an example. So typically, so here are the scattering angle in the center of mass frame for two different systems. This one's argon scattering from krypton atoms, and this one is argon scattering from xenon atoms. And both of these diagrams are qualitatively similar. So if you look at the forward scattering direction, that corresponds to theta equals 0. You see that the scattering is strongly peaked in the forward direction. Right, this is on a logarithmic scale, so there's lots and lots of atoms scattering in the forward direction. You also see that there are some peaks. And this peak out here, this highest angle peak, that's what's called the rainbow scattering peak. I'll explain what that means in just a minute. And then in between forward scattering and the rainbow scattering direction, you can see some oscillations. Right? Those are sort of the common features that you frequently see in these systems. Okay, so relatively broad maximum at what's called the rainbow angle, right here. And it angles between the forward angle, which is 0 degrees, and the rainbow angle, the probability oscillates. And then also, as you look at the backward scattering, right? Backward scattering would be theta equals 180. Basically, this distribution decays to 0. So the probability of backward scattering is very, very low. Okay, so why does it look this way? Well, basically, you have to consider the interaction potential, and then you have to average over all the possible impact parameters, and then that's how you have to think about this process. So if you look at the potential for interaction between two atoms, typically it's well fit by a potential in sort of a Leonard-Jones form, where at long distances there's no interaction. At relatively short distances you have a attractive dispersion interaction, right, leading to a minimum in the potential energy, and then at very short distances the interaction potential shoots up because you have electrostatic repulsion. Okay, so what does this look like if you consider different impact parameters? So let's first consider the case where, so maybe this is a krypton atom in green, and then in black I'll draw an argon atom. Okay, so in the first case, let's say you have large B much greater than the rainbow impact parameter. So if you have a very large impact parameter, then basically the two atoms, they're not going to feel each other very much, but right, when they're a long distance away, you have a slight attraction. So as the argon atom flies past the krypton atom, it's going to be deflected slightly towards the atom that it's scattering from. Okay? And so then the deflection angle, I'll call that chi, is going to be a small negative angle. Okay, what if you increase the impact, or I'm sorry, decrease the impact parameter, right? So in the next case, let's say you have an argon atom here, scattered from a krypton atom, right? And this B parameter, just to remind you, that's defined as this distance here, this is B, right? So in this case, the atoms are going to be closer together, they're going to be more strongly attracted, and as you bring them closer, the reflection angle is going to increase due to this attractive part of the potential, right? And at some point, this chi is going to actually reach its minimum negative value, right? The deflection is going to be maximum in the negative direction, and that point is what we call the rainbow scattering angle. So this is the rainbow angle. And if you bring the impact parameter any closer, then actually, instead of the scattering angle continuing to decrease in this direction, it's going to start going the other way, because you're going to start scattering off the atom, feeling the repulsive part of the interaction potential. So I'll draw an example of that. So if you have a much lower B parameter, let's say like this maybe, right? So this is B greater than, or actually, yeah. It's greater than B rainbow. In this particular case, I'll draw the glory scattering angle. So basically, you're going to feel an attraction, but then you're also so close to this atom, you're going to start feeling the repulsive part of the interaction, right? And so at this particular, in this particular situation that I've drawn here, the scattering angle goes through 0, and that's a special impact parameter called the glory parameter. So this is called glory scattering. And this one is called rainbow scattering. And here, chi as a function of B has an extremum. Yeah, it's at its sort of maximum negative deflection point. Okay, and then if you increase B even, I'm sorry, this should be B less than PR. Right, so if you have an even harder collision, right, with a lower impact parameter, then you start, chi comes around the other way. And then you start to have backward scattering angles. Okay, and so you can draw a figure, right? We can plot the scattering angle as a function of the impact parameter. And so if we draw this figure, what's it going to look like? So when the impact parameter is very high, right? So if this is, here's chi equals 0, right? So when the impact parameter is very high, what's chi going to equal? Well, when it's very high. Like the two atoms are not even close to each other. They're just going past each other, right? They're not going to deflect each other at all, basically, right? So, in the limit of really far separation, this chi is going to be very small. So basically, you start at 0, but then as B gets small enough that the two atoms are starting to attract each other, then you start going towards negative angles. But there's some extremum, right? Because at some point, B gets so small that the atoms start to repel each other. And so you go through an extremum, you start increasing, then you go through 0, and then you continue to increase. And as you go to really small impact parameters, the angle is changing very rapidly as you change the impact parameter. Yep. And so this particular point here, this is called the rainbow impact parameter. This one's called the glory impact parameter. Okay, but in a scattering experiment, we actually measure an angle which is the absolute value of chi, right? We can't tell whether it's scattered this way or that way. We can just tell what angle it was deflected from its original angle, and the problem is cylindrically symmetric. So we can only measure the absolute value of chi. And so if we plot theta equals the absolute value of chi versus B, then we just take the absolute value of this graph, and then that's going to look something like that, right? So here's the rainbow parameter, here's the glory parameter. Okay? And so now let's think about, what are the probabilities of scattering with these different angles? And in order to determine the probability of a certain angle, basically, you have to say, okay, well, every impact parameter is going to be equally likely in the experiment. So how many impact parameters basically lead to the same theta? Right? And so you can see there's all these impact parameters, anything greater than this point here, right? Basically the atoms are far enough apart from each other when they scatter that there's no deflection. And so most of the trajectories happen that way. That's why you have this big peak in the forward direction, right? Because there's many trajectories for which basically the atoms don't scatter at all. They just fly past each other. Okay? But then you also have this point here where the slope d theta dB, so when d theta dB is close to 0, then there are also many B values that give the same theta. Right, so there's sort of a range of B that sort of all give the same theta here. Right, whereas, if you're in this region, then, theta is really changing very rapidly with B. You're only going to get this theta if you get exactly this B. Right, whereas if it's changing more slowly, then many B's give approximately the same theta. Does that make sense? Okay. So dB, or d theta dB equals 0 at when B equals the rainbow impact parameter and when B approaches infinity, right? Here the slope also goes to 0. And you have many, many trajectories that all have the same, give the same theta. So therefore, the intensity as a function of theta, you would expect it to have a maximum, or maxima, at angles corresponding to the rainbow angle and at that angle corresponding to B equals infinity. Okay? Does that make sense? So just to be a little bit more explicit about the mechanism, how this works. We can take this graph that I drew and turn it over on its side. So I'm going to plot on the vertical axis the B parameter, and on the horizontal axis the theta parameter. Right? And so when B is high, theta equals 0. Then theta goes through a maximum at the rainbow angle, goes to 0 at the glory angle, and then it basically goes to 180 degrees as B approaches 0. Yep, so here's 0 degrees, here's 180 degrees, right? Here's theta rainbow. Okay? And so, what is this going to do in terms of the angular distribution, phi of theta? Okay? So, basically all these trajectories, anything higher than this B, these are all going to pile up, and they're going to give you a large value of theta, or a large value of I at theta equals 0, right? Large intensity at theta equals 0. That's then going to decrease as you increase the angle. But then there's also going to be a lot of trajectories right here where the slope is basically, well, in this way it's infinity, right? So you're going to get a maximum somehow here, right? Between the rainbow angle and 180, the slope of this graph is shallow, right? Meaning you don't have very much intensity, right? There's not a lot of trajectories over a range of impact factors that add up to give these angles out here. Okay, but what happens in between 0 and the rainbow angle? Yeah, here, yeah, so I showed you in the example that there's oscillation. Does anyone want to guess why? So what about this angle here? How many different B values can lead to this angle here? Right, there's 3 different trajectories that lead to the same result. And when you have a quantum mechanical system, anytime that's true, you have interference effects, right? So it's kind of like the double slit experiment where if there's two different slits that the molecule can go through and end up on the same spot on the screen, then you can have interference between these different channels, which leads to oscillations in the probability. And so basically you have these quantum mechanical oscillations due to interference from multiple different B parameters that give rise to the same scattering angle. Okay, so we can label this graph. This is the rainbow peak. And here you have multiple B values lead to the same theta, and as a result you have quantum interference. And oscillations. Okay. All right, so just an interesting fact. Why do we call this rainbow scattering? Well, the reason for the name rainbow scattering is because there's an analogy between atomic beam scattering and the scattering of light rays off of water droplets in the sky. And so if you look at the scattering of light off of a water droplet, then basically there are competing effects of diffraction and reflection angle. And as a result, if you plot, what's the trajectory of the light ray through the particle, through the water droplet, then you'll see that at a particular value of the impact parameter, the angle of scattering goes to a maximum, and then it decreases, it goes the other way. And so what that means is at this special angle where theta of B has an extremum, then you have opposing forces due to diffraction and reflection, and that leads to intense light scattering at this special rainbow angle. And it's exactly analogous to this case that we talked about with atom scattering. And so you get bright scattering of light at a particular angle. And there's a slight wavelength dependence, right? Because the diffraction angle has a wavelength dependence, and that's what leads to the dispersion of the rainbow into its different colors. And also, as you can see, like we've said, these scattering processes give us cylindrically symmetric range of angles, and that's beautifully illustrated when you look at a rainbow in the sky. It follows this circular arc shape. Oops. So, yeah. Question? Okay. All right, so just to be a little bit more quantitative, I'll just do this really quickly. Let's say, okay, we have this, let's say you have a particle scattering from another particle at a particular B, right? It's cylindrically symmetric, right? So if the particle comes in at another direction, but with the same impact parameter, right, you get this cylindrically symmetric scattering. And then let's say you come in with a slightly larger impact parameter, B plus dB, right? And then, then we're asking, right, so this is cylindrically symmetric with respect to phi. So, what range of solid angles is included in this, B plus dB range, right? After you integrate over phi, over the azimuthal angle? Well, the answer is d theta equals, okay, we have to integrate over d phi of I of theta times sine theta d theta, right? So this is equal to, so this integral is just 2 pi because it's symmetric, has no phi dependence. So that's 2 pi I of theta times sine theta d theta. And that's equal to 2 pi b dB, right? It's equal to the area of the sliver of circle between here and here if you rotate this diagram about the phi angle. Okay? And so if you solve this equation for I of theta equals b over sine theta times d theta dB. I'm putting absolute values because theta is defined so it's always positive. And this is proportional to d theta dB reciprocal. Right, so as you can see, anytime you have the reciprocal of d theta dB going to 0, right, or I'm sorry, d theta dB goes to 0, so the reciprocal goes to infinity, right, so you have this situation here. You would expect the intensity actually to go to infinity. But that doesn't happen in real life because we can't measure the angles infinitesimally precisely, and also due to quantum mechanical reasons, quantum mechanics doesn't allow the specification of an angle to be infinitesimally precise due to uncertainty principle. And so you see sort of a broadening of the distribution, but you see a peak where classically you would expect the distribution to go to infinity. Okay, just really quickly, I'll introduce the concept of inelastic collisions. So in an inelastic collision, they're also non-reactive, but you could have the excitation of an internal degree of freedom. And if you have internal excitation, that means that the total energy that's available to the scattering product is not the same as what was available to the incident molecules. And so, for example, if you look at NO molecules scattering from argon, initially in rotational state Ji, and the final rotational state of NO is Jf, right? That would be an example of an inelastic collision. And so I'll just quickly show you an example. So in this example, here's an overall picture of the incident molecular beams. This is taken using ion imaging. The NO is coming this way, and the argon atom is coming this way. Okay, and so here is the Newton diagram for this interaction. And if you look at an image where you only ionize the NO molecules in particular J states, then you can look at the product distribution corresponding to particular final internal energy states of the NO molecule, right? Different rotational states. And so if you look at low J, you sort of get a broad sphere that's possible, but the scattering is highly concentrated in a particular direction. And if you look at more higher, right, rotational energy of the NO, you end up getting a sphere that is smaller, right, because there's less energy available to translation if you put more energy in internal degrees of freedom. If you look at a very high J state, the scattering distribution is very highly concentrated. Okay, and just a few facts about this picture. So yeah, so as the final J increases, the diameter of the scattering Newton sphere decreases because there's less available energy for translation. As the final rotational energy increases, the distribution of scattering moves from the forward part of the scattering sphere to the backward part. So you can tell, right, it's actually, the location is moving from forward to more backward. And the reason for that is that weak collisions involving large impact parameters, they are less likely to change the J state by very much, but whereas low impact parameter, very hard collisions are much more likely to strongly impact the NO molecule, lead to a rotational excitation, right? And those are the collisions that also are more likely to cause backward scattering, just due to momentum conservation arguments. Okay. And also the scattering tends to be localized at specific angles. These are called rotational rainbows, which are basically the angle for which there's an extremum of theta versus B for a particular J, for a particular J final, right? You could redo these diagrams for a particular J state, and you'd get a different rainbow angle for each J state, basically. Okay, that's all we have time for. Any questions?